Hi, I'm Steve Sobek, owner of amysflashcards.com. The purpose of this video is to show you how to use graphing strategies on a TI-84 calculator to solve equations. There are two graphing strategies. We'll cover one of those strategies here in part 1, and the other strategy we'll cover in part 2, a different video. But before we get into our first problem, I'd like to develop some foundational concepts. We'll do that by looking at a very simple linear equation, and of course all of you who've had algebra know how to solve that by adding 6 to both sides and dividing both sides by 2 to give you the solution. But I also want to remind you what a solution is. A solution to an equation is a value for that variable that makes the equation true. Sometimes we call solutions truth numbers to help remind students what they are and how to check your answer. You know, if you know what the meaning of a solution is, then you know how to check your answer. Plug it back in and see if it makes the equation true. So even students who've never had algebra, but they know what a solution is, could probably just trial and error, plug in a few numbers, and eventually find that 2 times 3, if you use 3 for x, 2 times 3 is 6, and 6 minus 6 is 0. 0 equals 0 is true, and 3 is the value for x that made that equation true. So 3 is the solution to that equation. Okay, never lose sight of what a solution is. Now, let's take a look at the graph of y is equal to 2x minus 6. It's a linear function, so it's a straight line as we expect. And remember that the points on this line represent ordered pairs that are solutions to this two-variable equation. 0, negative 6 is a solution. 1, negative 4 is a solution. 2, negative 2. 3, 0. 4, negative 2. 5, 4. Okay, 5 for x and a 4 for y. That would make this equation true. And those are just a handful of the solutions, and there are millions and millions of solutions even on this current viewing window. And we understand that these lines continue indefinitely in both directions, and so there's millions and millions of more ordered pairs that make this true. Now, with respect to our goal of finding the solution to this equation up here, what part of that graph is relevant to that endeavor? Let's think about that. A solution to the equation is going to be a value, since the right side is 0, we want a value for x that makes the left side work out to a 0. So with our function down here, we want a value for x that makes this expression work out to a 0, which is our y value. Where on the graph is the y value a 0? Well, it would be a point that's on the horizontal axis. It would be this point right here. That is the point that has a y-coordinate of 0. And what looks like the solution, well, just going by looksies, it looks like positive 3 is the value for x of that particular point. Well, the x-coordinate of that point where the graph passes through the horizontal axis is the solution to our equation. And that's an important concept, and I want that to make sense. Let me get rid of this here and summarize. The x-intercept, which is the x-coordinate of the point where the graph passes through the x-axis, is the value that makes the expression equal to 0, and thus is the solution to this original equation. All right, let me see if I could generalize that. Okay, in conclusion, what have we learned? We've learned that if we have any equation in the form of f of x equals 0, See, this method requires that the right side, or one of the sides of the equation, be a 0. Like our previous example, 2x minus 1 equals 0. If we take any equation of the form f of x equals 0 and consider the graph of y is equal to f of x, like y is equal to 2x minus 1, all right, then the real solutions to this equation are the x-intercepts of this function. The x-intercepts, which are also referred to as the zeros of the function. Those are the values for x that make the y value 0. These are the values for x of those points where a graph passes through the x-axis. So the solutions to the original equation would be these x values. We would take that and put that in the solution set. Take this x value, put that in the solution set. Take this x value and put that in the solution set. And those would be this particular, based upon this particular graph, we would have 3 solutions to the equation f of x equals 0. Solutions to an equation are also referred to as the roots of the equation. The roots of the equation. So the zeros of the function are going to be the roots to the original equation that we're trying to solve. I used to tell my students that concept is so important. I don't want you to eat, sleep, drink, or breathe until you firmly understand that. And so I hope that you too might review the video as many times as necessary before you progress, because that's one of the most important concepts that you'll learn in algebra. All right, let's move on to our first problem that we're going to solve today. Okay, here's example number 1. The first equation that we would like to solve using a graphing strategy. It's a cubic equation, a third-degree polynomial equation. Before we graph the corresponding function, y is equal to f of x, just a few comments. We know that all third-degree polynomial functions will pass through the x-axis at least once, because the lower extreme values for x and the upper extreme values for x are going to take off in different directions. It's feasible that the graph comes from below, loops back down, and then comes back up like this. That's a possible scenario. And in this case, we know that since the leading coefficient was positive, 0.3, that it will eventually take off for extremely high values for x. It's going to shoot for the moon. And that means the other end, for very, very small values of x, it's going to shoot downward, aim downward. We're not sure where this little loop is right here. If the graph looks like this, then we will have only one solution to our equation, and that would be the x-coordinate of this point right here. All right, now let me back up a little bit. If the graph comes up through the x-axis and back down and then back up again, it's feasible that our equation is going to have 3 different solutions, because the function y equal f of x passes through the x-axis 3 times. All right, so let's enter this function, into the calculator and take a look at the graph, and then we'll show you how we can find those zeros of the function, the x-intercepts, those x-coordinates of the points where the graph passes through the horizontal axis. All right, so on the calculator, we want to type in the function. I'll hit the y equal 2 key and pause the video and restart that whenever you have yours typed in. Okay, now that you have it typed in, let me just show you how I would type that in. Once you hit the y equal 2 key, we want to clear out any functions that may have been defined previously. And let's type in 0.3. Here's your decimal point. 0.3 x raised to the third power. Remember, we cube things through the math menu. Math, number 3 is cubing. Hit the 3. You could have also used this exponentiation key, the caret, raised to the third power. Either way. Minus 3x squared, minus 3x, and here's x squared button right here, plus 2x, plus 7. All right, and why don't we begin with zoom 6 so that we all have the same viewing window when we begin this with this graph. Okay, here we can see a portion of the graph. The last video that I did, lesson number 2, focused on achieving a suitable viewing window for the graph, and so I don't want to spend too much time with that today. But we could see we could probably get away with going down just to maybe -3 on the x-axis. We're good in terms of x max. We're good up here in terms of y max. We need to go a little bit lower to see the bottom of this graph. Not that that is going to be critical to this particular application, but let's get some practice showing the full graph there. So it's hit the window button, and let's decrease x min to -3. Hit enter. X max is good. Let's hit the down arrow key to highlight y min. I'm not sure how low we need to go, but perhaps why don't we try negative 30 for starters. All right. Y max seems like that's okay. Let's hit the graph button and take a look at this. All right, that's a good viewing window. We're seeing all the relative max and min points, and we're seeing all of the intercepts. Should we need to be concerned about maybe this graph looping back up? No, a third-degree polynomial function is going to change directions no more than twice. It already changed directions once, twice. It's changed directions twice. It's not going to change directions a third time. It'll never have more than 3 x-intercepts. All right. So now the question is, how do we find, since we're concerned about the x-coordinate of that point right there, how do we find that? We know the y-coordinate, it's 0. But what is the x-coordinate? And here's how we do that. We go in, we hit the second button, this blue button up here, second, and right above the trace key we can see it says calculate. So hit second, calculate, and from this menu we're trying to find the zeros of the function, and that would be number 2. So hit a 2 on your calculator, and it doesn't automatically give you the zeros of the function. These ordered pairs you see at the bottom, that of course 3.5 is not a zero of the function. That's not a value for x that makes the y 0. It's way over here. We have to answer 3 questions before it gives us those coordinates. It wants to know which zero of the function you're going after, which intercept. So I'm going to hit my left arrow key and keep hitting that until we get a little bit to the left of this point, because that's prompting me for the left bound. So it wants to know, you're trying to find the zero of the function between what boundaries? Well, you know, anywhere to the left of this point here is a good left boundary. Hit the enter key to accept that as a left boundary. And then hit your right arrow key until you've gone a little bit to the right of that point. It doesn't have to be very far. And hit the enter key. And now you've established your right boundary. You can see these dotted lines here with these arrows. We're looking for the zero of the function between these boundaries that you've established. One more question that it's asking us, and that is, what is a best guess? It wants us to hit the left arrow key to get back somewhere close to the intercept. You could be anywhere in between, doesn't matter, and hit enter. And finally, it will give us the 0 of the function. Here's the x value that makes the y value a 0. And so I'm going to write that down, negative 1.177. I'll just round that to 3 decimal places. And then we want to go after the other intercepts. We do that in the exact same manner. We hit second, calculate. We're trying to find a 0 of the function. We'll choose number 2. And hit your right arrow key. And maybe stop somewhere so you're still to the left of, we're going after this point right here. So he's to the left of that. Where it's blinking right now is to the left of that point. Hit enter to accept that as the left boundary. Hit your right arrow key until you've gone somewhere to the right of that point, and hit enter to accept that as a right boundary. And now it knows that it's going to find the 0 of the function somewhere between these 2 points. It looks like it's between 2 and 3, closer to 2. Hit your left arrow key, so you're kind of close to the solution. Hit enter, and now it's right on the x-axis. It shows the coordinates down here. Of course, the y is a 0. We're concerned about the x value. Let's write that down, round it to 3 decimal places, 2.211. And we've got 2 out of the 3 zeros of the function. I suggest that you pause the video and get this final 0 of the function, and then I'll restart the video and watch me as I do that as well. Okay, now that you've restarted the video, I'm going to hit second, calculate again. I'm going to choose number 2. I'm trying to find the 0 of the function. I'm going to hit my right arrow key to get over near the final intercept. And that looks like a good left boundary. Hit enter to accept that. Hit the right arrow key to somewhere to the right of that point. Hit enter to accept that. And move it to the left. And you don't have to be really very close. Anywhere in between is fine. Hit enter. And it will give you the coordinates of the final 0 of the function. Let's round that to 3 decimal places. 8.966. Now, don't be alarmed that this doesn't say 0 like it did the last 2 times. That is virtually 0. Remember, when you see the capital E, this would be lesson number 1, the very first TI-84 instruction video. We talked about scientific notation. 1 times 10 to the negative 12th power is in a very, very minuscule number, virtually 0. Okay. All right. So, anyways, those are the 3 values. Let's go back over here, and let's write our answers down in the answer slot. And we've just solved our first problem. We've found the 3 real solutions to this 3rd degree polynomial equation, this cubic equation. That wasn't too hard, was it? All right, let's move on to a few more examples. All right, here's problem number 2. This will be a projectile problem. We're told that a cannonball is shot upward at an initial velocity, vertical velocity of 50 feet per second from a height of 23 feet. How many seconds will it take the cannonball to hit the ground? All right, well, suppose here we have the formula that the height as a function of time is going to be equal to negative 1/2 or negative 0.5 times the gravitational constant. On the Earth, that would be 32 feet per second squared, times the square of the time in seconds, plus v sub 0 t plus h sub 0. where v sub 0 is the original velocity, vertical velocity, and h sub 0 is the original height. Notice that they don't give us the horizontal velocity component because that is irrelevant to this particular question. As you recall from, if you've had physics, then you know that if you were to throw a ball horizontally at a height of 6 foot and drop another ball at this from the same height of 6 foot, if they both enter free fall at the same time, they'll both hit the ground at the same time. The horizontal velocity imparted on the ball does not impact the time it takes to reach the ground. And so in trigonometry, we'll have to ask students to calculate the vertical velocity component using trig functions. But we're just going to give that to you. And if we make the substitutions, if we put a 32 in place of g, half of 32 is 16. The original velocity is 50 feet per second, and the original height is 23. And we want to know, when does it hit the ground? So that they're indirectly, they're not explicitly giving you a number there, but they're hoping that you understand that the height when it hits the ground is 0. They're saying, what value for t is going to make h of t 0? And so we put a 0 in place of h of t. That's what we're trying. If they're asking, when does it hit the ground, we put a 0 in for t. So now we have an equation. It's of the form that we want. It's equal to 0. This must be a 0 to use this particular method. We have to have a 0 here. And only then will the zeros of the function be our solutions to that equation. All right, so we want to graph y is equal to this function. And so let's go ahead and type that into our calculator. Let's hit the y equal 2 key and hit the clear button to clear that out. And you could tick along with me if you like. Negative 16. And of course we're going to use x for our variable, x squared, plus 50x, plus 23. And let's start with a zoom 6, just so that we all have the same graph from the very beginning. Okay, now we understand that this is a quadratic function. A quadratic function is parabolic in shape, and since the leading coefficient was negative 16, if it's anything negative, then the parabola is going to be facing downward. And so what we're not seeing is the top of the mountain. So we're going to have to adjust our viewing window so we could see the top of that mountain there, and we could even adjust it. Certainly we don't need to go more to the left than negative 2 seems more than sufficient. And what is this? 1, 2, 3, 4, maybe 5 to the right. Let's go ahead and adjust the x-axis right now. Hit the window button, and let's go from negative 2 to positive 5 on the x-axis. Hit the graph button, and that will improve things somewhat. And we could trial and error, just kind of guess, what to use, or how high do we think this projectile would go. But remember, in my second lesson video, I told you how the table feature, which allows you to, like a machine gun, make rapid fire substitutions, just to get an idea of how high this function goes. It occurs somewhere, around 1 second, 2 seconds, or it's going to be maxing out. So let's go into our table feature and do some rapid fire substitutions just to give us an idea of how high this function is going, so we know how high to make the window. All right, so we're going to hit second table. Let me delete these values that were here from the last video. All right, let's start substituting some values for x. You know, the x represents time in seconds. So after 1 second, we've reached a height of 57 feet. After 2 seconds, 59 feet. 3 seconds, 29. It's coming back down. So it's probably going to max out somewhere near 59, maybe low 60s. Let's set our maximum value for y. Let's set that at 70. All right, so let's hit the window button and hit the down arrow key to highlight y max. And it's 70. And we might as well change y scale to 10, just so that we put a notch at every 10 units, so we don't have so many notches that it looks like a fat line. Let's hit the graph button. And here we have a nice viewing window for our parabola. And again, if that adjustment on the viewing window seemed a little bit rushed to you, go back and view my lesson number 2, which focuses on getting a suitable viewing window. And we go through this much slower and show many examples. All right, we're concerned about the x-intercepts. Where this graph passes through the x-axis, that is the solution to the equation. Now we have 2 x-intercepts. How many solutions will we have to our original problem? You might say, well, we have 2. And certainly the equation will have 2 solutions, one negative, one positive. But remember, there's a implied domain of the variable. Well, it's understood implicitly that we're looking for a positive value for time. We're not going to say, oh, at negative 0.3 seconds it hit the ground. Okay, positive values would be in the implied domain, and so this is the only zero of the function applicable to this particular word problem. So let's go ahead and hit second calculate, and we want to find the zero of the function. Choose number 2. Hit the right arrow key to get over there, a little closer proximity, but that's close enough. Hit enter to accept that as the left boundary. Hit your right arrow key some more to get somewhere past the point. Hit enter to accept that as the right boundary. Hit the left arrow key somewhere in between and then hit enter again. And here, let's write this down. 3.532 seconds would be the x-coordinate that makes the y. Remember, this is virtually 0. And thus, this is the number of seconds it would take for it to hit the ground. Let's go back over here. And we could just write that in. 3. Did it say round? No. 3. Let's round it to the nearest tenth of a second. So at about 3.5 seconds, it takes that cannonball to reach the ground. There's example number 2. All right. Again, very easy to find the x-intercepts using second calculate once we get a suitable viewing window for the graph. I know what you're thinking. Give us one more example. And that's what we'll do. We'll go through one more example, and that will conclude this video. Okay, here's our third and final example that we're going to give today. It's going to involve an exponential function. Suppose $15,000 is invested and no future contributions are made to the account. We call that a lump sum investment problem. If we assume a growth rate of 8% per year, how long will it take for your money to triple? In other words, become $45,000. We're to solve this with the graphing method. Right? Obviously, if you've covered logarithms, you'll want to jump in there and solve this with logarithms. But suppose you haven't covered that yet, and so we could still get the answer using our graphing strategy. remember that the amount in your account is going to be equal to the original principal times 1 plus the interest rate in decimal form, all raised to the t power, where t is the number of years that have transpired, and the number of compounding periods. And since we're compounding per year, then t is the number of years. So our equation is going to be the original principal times 1 plus 0.08 is 1.08 raised to the x power. We want that to be equal to triple 15,000, which is 45,000. Now this equation is different from the previous two examples in a very important way. The other examples all had a zero on one side of the equal sign, and this doesn't. Our method our first method for solving equations with the graphing method requires that one side of the equation be a zero. So rather than abandon ship, we just take an extra few seconds to make this sign zero. Subtract 45,000 from both sides, and then that will give us 0 on the right, and that will give us this expression on the left. Now this equation is in the proper form for using our first graphing method for solving the equations. We want to graph y is equal to this particular expression. So let's go ahead and hit the y equal to key, and we'll type that in. Actually, before we graph this on a calculator, let's take just a moment to think about an appropriate viewing window. Obviously, with numbers like this, it'll be futile to use a standard window from negative 10 to positive 10 on both of the axes. So let's think about something that might be reasonable for starters, and then we can adjust after that. When x is a 0, anything to the 0 power is equal to 1, we're left with 15,000 times 1, or 15,000 minus 45,000, or negative 30,000. So it's going to pass through the, let's change colors here. It's going to pass through the y-axis down here at negative 30,000. And it's going to grow exponentially. And so it's going to be, going uphill like this. And let's think about how far we need to include this point. How many years do we think it's going to take to triple our money? Now, those of you who know the rule of 72, then they know that the money is going to double in 9 years. 72 divided by 8 is 9, and that's a little trick for knowing how long it takes your money to double based on a certain interest rate. So it's going to be more than 9 years, and it's not going to be it's going to be less than 18 years because your money's going to double again. So you'll have 4 times as much money in 18 years. So somewhere greater than 9, maybe we could say 16 might be a good starting place for the maximum value for x. We're really not concerned with negative values. So let's let's type in our function first. All right, let's go ahead and type in the function. You could type along with me. We want 15,000 times the quantity 1.08 raised to the x power. Hit the right arrow key to get out of the exponent. Minus 45,000. And before we hit enter, let's go in and make sure that we have the window, that you have your window set up similar to mine. Recall that we estimated that the x max would be less than 18 years. We're going to triple our money. We knew it had to be more than 9, so 16 seems like a good starting place. y minimum, we saw that the y-axis had, the y-intercept was negative 30,000. So let's go a little bit below that, negative 40,000. And set y max to 10,000, so we remember when we use our procedure, we have to move above the horizontal axis, and so we need a little bit of room above that to do our procedure. And y scale, let's set that at 1,000. Put a notch at every 1,000 units. If we left it at 1, we would the y-axis would look like just a very thick, fat line. Would have so many notches. All right, let's hit the graph button and see what this looks like. Okay, here it started at negative 30,000, and it's exponentially growing, and it's passing through the x-axis right here. You could actually go ahead and finish the problem and then restart the video and watch me do it. All right, now that you've restarted it, I'm going to hit second, calculate. You remember that now. We're seeking the zeros of the function. We're going to choose number 2. And we're going to hit our right arrow key, but stop short so that we're still somewhat to the left of that intercept. Okay, that looks adequate. Hit enter to accept that as the left boundary. Hit the right arrow key so you go somewhat to the right. That's good enough. Hit enter. And best guess, I go anywhere in between, and hit enter again. And here we have our solution. Remember, the solution is the x-coordinate. We're not concerned about the y. We know what the y-coordinate was going to be, 0. But the 0 of the function and the solution to our original equation is the x-coordinate of that point. So let's write that down. 14. Let's round that to the nearest tenth of a year. About 14.3 years. So let's write that down. 14.3 years, our money will triple. All right, so there you saw how we would use the graphing method, one of the graphing methods on a TI-84 calculator to solve equations. And second, calculate, left bound, right bound, best guess. It all is really very simple. And even though the equations might get more and more complicated as we look at, we're looking at exponential here, but if we had logarithmic equations or trigonometric equations or radical equations, no matter, it's still the same good old second, calculate, left bound, right bound, best guess, and we can get solutions very, very easily, as long as we're able to first manipulate our equations so that one side is equal to 0, and then graph y is equal to that other side, that expression. We could solve some pretty nasty equations pretty rapidly using this graphing technique. I hope that you stay with me on the for the second part 2. We'll show you another graphing technique. We'll attack this same problem and maybe have graphs that look a little bit more meaningful for that. And I should also mention that those of you who've covered logarithms, of course, would just take the log of 2 and log of 3 divided by the log of 1.08, and that would also give you the same answer. Let me hit second quit. And I know that many of you have done this already. The log of 3, close the parentheses, divided by the log of 1.08, close the parentheses, and hit enter, and we'll still get the same, about 14.3 years. So anyways, so there's our first video on using graphs on a TI-84 to solve equations. Thank you for joining me today. I hope you found that helpful.